All right. So, hello everyone. I think we are live. Can anybody confirm this? Okay. Hi, good evening. So, what's up, guys? My name is Viraj. I am an educator in TLE, specifically handling level 1. And today, of course, we'll be having our demo class on a very, very famous topic that is Intro to Time Complexity for competitive programming. I hope everyone is doing fine. All right, so I'll be watching you guys in the chats over here next to me on my phone. So do make sure you guys pop up any doubts you have even during the class. I'll try to do them at the very end. And yeah, so should we start? I think I'm audible and I'm visible. Can anybody clear this out? And by the way, is this screen also visible to you guys clearly? I think my screen should also be visible. I hope this PPT is clear. Time complexity. Yes. Okay, great. Okay, so actually, before we start off, a quick thing about what we are and what do we do. So, what is exactly TLE Eliminators 12.0? This is something you guys should know. Anybody who's watching us right now, you guys should know. So, TLE Eliminators 12.0 is actually our flagship course in TLE of the 12th edition, which we have launched. Courses, I think, start in the next few days, and this is bifurcated into majorly 4 levels. This basically covers everything that you have to experience on your competitive programming journey, right there from a beginner level to take you up to a pre-intermediate level, to an intermediate level, to a advanced level. So we have a lot of different new concepts which are something that are not out there in free content, which is something that are not taught very easily, all in terms of how competitive programming sees them. Stuff like interactive problems, number theory, dynamic programming, DSU, segment trees, Fenwick, and so on, so on, so on. So it's a lot of big collection set of things that we handle over here in DLE, and we have 4 levels. So definitely check them out, and please be part of the 12.0 batch as it is. This would be again a definite boost to your competitive programming journey. So if you are totally looking out for some guidance, you're looking out for something, some growth in this, make sure you actually be part of this whole thing. Okay, great. Should we start? I think let me just, yeah, great. So I think we are all clear. uh yeah, my page is clear. All right, so let us go. So first of all, the topic is time complexity that comes in CP, that is competitive programming. So technically, time complexity, we like the name we have, TL eliminators. Why do we actually want to learn or understand time complexity? Very simple stuff. If you are not aware of how an algorithm works in terms of what time does it take to execute it, most probably you will run into a very sort of a term that pops up in competitive programming a lot many number of times, that is called TLE. All right. How many of you guys are aware of this? TLE, that is time limit exceeded. And we as TL eliminators have the target only to actually eliminate this. So hence you have a very important topic that comes in time complexity. If I understand this, then I know I am very clear on uh, a lot of algorithms, how will they work, and the code that I might write for a problem that I'm solving, will that get me an accepted solution or not? It might be getting me a TLE, but if I have a knowledge of time complexity, that's a plus point. Okay, so this is not again limited to how you do competitive, like how do you, like this topic is not limited to CP, but this is also a topic that is very important for your overall DSA. And by the way, very important for anybody who's looking out in interviews. This is like one of the top questions that is asked after every problem is solved in interviews. So you solve a problem, you make a solution, that's all good to go. But what happens when you actually finally complete the problem? The interview is going to be like, okay, great, tell me the time complexity of this problem. So you need to have a grasp on this topic very acutely, and that is why this becomes a very rudimentary topic. Hence this is part of level 1. And for anyone who is looking out to understand this topic fully and similar topics, definitely check out level 1 in TLE 12.0. Great. So is everything good to go? Just give me one more. Uh, yeah, okay. So I think I'm audible, and Anupam has also said. Great. So I'll move on. What is the goal of today? So first of all, of course, we have to understand time complexity. We want to thoroughly understand why is this important, what is happening over here. So I'll give you a general brief in this. So you're sitting on your computer, you start coding, and you say, okay, I wrote like 4 or 5 lines of code. And this 4 or 5 lines of code, if it's actually solving something in computer analogy, we actually call this algorithm. Okay, this is known as an algorithm. And once you have written this algorithm, it's very, very important for you to understand that this algorithm might run in some sort of a time order. Now, typically, when we talk about computers or when we actually try to report time complexity, somebody might ask you, okay, tell me this number of seconds it's taking for you to run, or maybe it's number of milliseconds that it's taking you to run. So that is all a very far-fetched sort of notation when we actually tell what sort of a time complexity is there for algorithm. But in a very general order, when somebody asks us, do you want to report this in variable formats of the variables you could have taken in an algorithm, this is where time complexity comes into picture. To be very specific, time complexity governs the parameters of how you represent your algorithm in terms of the time it take in variable formats. So this is basically what time complexity governs. And to actually represent time complexity, we use a big O notation format. Now, big O notation format is not exactly, when we write big O, it's not basically O or it's not a zero. It's just an oval shape structure that we draw, something like this. And we called it big O because it's almost looks like a capital O. And then we have like two braces that open and close. And inside this is what we represent finally to tell, okay, in this sort of parameter is what I followed. And my algorithm could have been represented as big O of this, let's say O of n, O of n square, O of m, O of k, whatever is the variables I try to take. This is what I finally represent. So this is the big O notation that stands for the time complexity. This is going to be a second goal. How do we understand big O and other notations? Then our third goal is going to be, how do we evaluate a time complexity for an algorithm? So we are going to have fun quizzes. You guys will be open to the chats, do response, and tell me what answers do you feel are going to be there. I'll be popping up some quizzes. We'll be evaluating time complexities of looking at an algorithm. And then this is the most important and fun part of this class is how do, after understanding all the general paradigms of time complexity, tomorrow if I sit down and solve a problem, how do I get that intuition that, okay, I could have solved this problem during the contest using this algorithm? Or basically, what would have been the expected time complexity of this problem is another sort of a goal that we have to cover today. So it would be sort of a cheat sheet. If you actually cover this out, you will have full grasp on, if you look at a question, you might start getting intuition that, okay, I was taught in this class, I think I know the expected time complexity, so maybe I want to run this sort of a solution in this, and it might work. So you will be heading towards the right direction if you understand and expect the time complexity of the logic or the question pre-hand before you have even started the code. Okay, great. Is everything clear, guys? Am I audible up till now? Quick yes in the chat, possible. Okay, so I think I'm audible clearly. Yes, let me just go back. Hello, hello, hello. Yes, I'm audible. Correct. Okay, great. Cool. So let us move on. So now that we have understood what is today's target, when we actually talk about the algorithm, so when I talked about like writing 5 lines of code and actually representing that as an algorithm, what comes into picture is, okay, what is the smallest sort of an operation you could have executed in the computer? Let's say you just hand over him the very small, you hand over a computer a very small task. You just say, okay, add 2 numbers or maybe divide 2 numbers. So all this elementary sort of operations, elementary by the physical meaning is the tiniest operations that you can perform in your computer are known as elementary operations. This is the base of what time complexity finally expands to, and an operation that takes constant time is called an elementary operation. Now what do you mean by constant time? Constant time simply means O of 1, big O of 1, where 1 inside actually means just one sort of a iteration. You can say it's not exactly 1 second or 1 millisecond, nothing like that. It's basically like one iteration of one elementary operation that you took. So that 1 basically denotes one elementary operation. Now if I could have written this O of 5, that means 5 elementary operations. O of 10, that's 10 elementary operations. But because I'm talking about the basic most elementary operation, it's going to take O of 1, and O of 1 overall as a time complexity is called constant time. So any algorithm that follows only one elementary operation, you just take one operation to execute it, will be called a constant time based time complexity algorithm. Okay, I hope this is clear. Great. Okay, so let's move on. So now again, we have some examples of what is elementary operations, and we start off with very basic stuff, that is arithmetic operation. So arithmetic operation basically means just doing the most basic mathematics. You do plus, minus, divide, and so on. So it basically comes like a plus b. You do like a minus b, something like, yeah, a minus b. That is all good to go. And maybe you create a into b. That is also great, and so on, so on, so on. So this is like the basic arithmetic operations you do, and they are called the elementary operations. Now, second example is comparison of primitive types. So now, primitive data type is it's like a theory, some sort of a theory in computer science, where primitive data types are data types encapsulating int, float, double, all those standard sort of data types you see. And if we do a comparison, what do you mean by comparison? Let's say I tomorrow ask you, okay, there are two integer numbers. Tell me which is the largest. So you basically do a relational operator check. You say, okay, is A less than B? Is A greater than B? Is A equal to B? All this comparison sort of a stuff that we are doing in the, again, primitive data types is again an elementary operation. Okay. And then the third example is, what about we have input and output of the primitive type? So let's say you just take an input of a number, you take an input of an integer, and you take an output, you finally give an output of that integer, you print that to the console. So that should be important, that okay, I have used constant amount of time to take the input and the output, considering it's a primitive type. So you take an input of an integer, a float, a double, all those primitive types, that is basically elementary operation, it's constant time. So I can write this simply like this. You have like int a, and then you create something like a sin a, and this line of sin a is basically constant. Okay, any doubts, guys, up till here? I hope everything is clear. Great. So now, in this competitive programming sort of a space, there is a very important thing that we have to always remember. Typically, in a computer, like it might be very dependent on which sort of a computer you're using, what sort of bit capacity it has. Maybe you are using a quantum computer, so that's not the point. It's like a very generalized thing that we remember. Specifically with regards to the Code Forces, Code Chef, and online judges platform servers, what sort of operations do they maintain? 10 power 8 operations is actually taken as 1 second. That means if you perform 10 power 8 elementary operations, you will be totally requiring to run that test file or run your code 1 second. Okay. So now 1 second is very, very quick. I know that part, but the point is we actually try to create solutions that are even faster than 1 second sometimes. So that's a very, very unique thing that we try to do. And that's actually the beauty of CP. Okay. So now if I, let's say tomorrow say you that, okay, in this problem, you were allowed 3 seconds to totally run your test case, then you will be like, okay, then maybe I'm allowed, since 10 power 8 is 1 second, if I'm allowed 3 seconds, I'll be allowed 3 into 10 power 8 elementary operations. And this becomes a comparison check for you. Why? Because when we later on calculate time complexity and we plug in the variables, we can compare that, okay, I put this much n, this final n gave me, let's say, 10 power 6 order, and I could have gone till 10 power 8 order. So do I think this will work? Yes, this will work, because 10 power 6 is less than 10 power 8. So this becomes a, sort of a metric check, or like a very base check for which I can compare and be sure that I'll not get a TLE. Okay. So for terms of time complexity, usually what I've seen is 1 second. And then I'll just add for your extra knowledge, space complexity also sometimes comes into picture. That is 256 MBs is what normally platforms allows. This is in terms of the space that you consume. Okay. Cool. I'm not sure if my chat is free. So can you guys put a quick yes or something in the chat so that I'm audible and clear? Everything is going fine. Okay. Thank you. Thank you, Sean. Thank you, Songbit. Okay, great. So let us move on. I hope elementary operation was clear. So now we have a very, very simple quiz for you guys. I hope everyone tries to respond to this part. Now that you have understood elementary operations, can we have a simple yes, no quiz on, do you think the code has is an elementary operation? So let's talk about the first quiz. So this is the first example, a simple yes or no question. we are taking input of four integers in this a, b, c, d. And when you actually done that, you are trying to take like you're trying to print a plus b into c by d. So do you think this everything that we are doing right now is an elementary operation? Yes or no, guys? Yes, great. Cool. So this is of course an elementary operation. Why? Because we understood from the previous example also, if we talk about arithmetic operations, then we are all good to go in terms of elementary operations. So this is an arithmetic operation, right? Doing plus, division, multiply, and all that. So why not? This is of course an elementary operation. Great. What about example number two? You take input of two strings and then you compare. Is s less than t? If it is, then you print out. So do you think this is elementary operation? How many of you guys think yes? I mean, we are doing a relational check, right? We are comparing. So do you think it's yes? Yes, again. Okay. Anybody else? Because of comparison. Okay, makes sense, makes sense. Great. So Amish is saying no. Okay, so we have a yes and no. Great. So we have a yes, then we have a no again. Okay, so it's a bit confusing. Let's actually cover this. So this is actually a trick. We like remember the line over here. We are talking about comparison of primitive types. Now this comes as a theory concept. You can remember this now since you understand what's the mistake over here. String is not a primitive type. Okay, very very important part. String is not a primitive data type. String, if let's say tomorrow, let's say my name is Viraj. Okay, and let's say I have a name song with. Okay, so now what will happen is if I say that I want to compare these two strings, basically s is less than t, then this is not going to be an elementary check. Why? Because in the computer, what will happen is that computer is going to go to every character one by one and make a comparison. Okay, is V and S same? Okay. Is I and O same? Next letter? No. Is R and N same? So on, so on, so on. And this sort of a comparison that has been done, it is making me run a algorithm on all the characters. You can understand, right? I'm covering the characters from V to J, or basically S to T, which means that if let's say my string is longer, maybe it's of 1,000 characters, then maybe I'm covering 1,000 sort of checks in the character types. That means when I actually write s is less than t, string check being not primitive can be understood by saying this is not at all a elementary operation. This cannot be termed elementary. Okay, is this clear, guys? Very very important. I hope this should be clear. Any doubts? So first answer becomes yes and the second answer becomes no. Clear. Okay, great. So now we have the final thing. What is time complexity? So as I explained, time complexity is a function to describe the approximate amount of operations an algorithm requires for the given input. You can call this as notation also, right? We use the term notation also. That's pretty much simple. Notation described to approximate the time of operations an algorithm requires to perform. Now we can calculate approx execution time of the code using time complexity and constraints. Okay, so this is the general meaning of this part. Of course, as I explained previously, you have some lines, you try to run this and everything. This is what is going to be the notation. Now, the important thing to understand in this is that, as I mentioned previously, let's say you write like 4 or 5 lines of code, and somebody asks you, what is the millisecond amount of time you actually run this? You'll be like, oh, maybe like 5 milliseconds. But when we actually want to represent this in a variable format, we don't use all the structure. We say, okay, let's say in this, like I'll write a very basic code. Let's say you have an array. And let's say then you write a for loop and you simply take the input in this array. So input a of I. Now what will happen is, let's like I like send off these two variables a of I. Now what will happen is, if I ask you what's the time complexity you are utilizing for this piece of code, for like for just for a saking part, I'll tell you that time complexity for this is simply O of n. Why? Because I'm running a for loop that is running from 1 to n. So it will, if you have let's say n is 10, then you will run for loop 10 times. If n is 20, you will run 20 times, and so on, so on, so on. But now if I know my code is represented in this manner, and let's say for, like, let's say n was 1000, for some test case n was 1000, so maybe you figured out that for 1000 case this piece of code was running in 10 milliseconds. So tell me, will it be right for you to tell your interviewer or tell me or tell yourself to be the first place that you are running your logic or your overall logic is actually of 10 seconds, 10 milliseconds? No, right? Why? Because what if n changes to 1000 to 10,000? Of course, this is going to change. So can you not imagine that it's always better to report the time complexity in terms of variable rather than a constant time? That is why this is a function, this is a notation rather than a constant value. So it would be better that I report my time complexity as O of n, correct? O of n would make much more sense, because now if n grows, if it depends on n, then will you also tell the meaning of the sum of, yeah, definitely, Aditya, I'll tell that part. This is a very, very important point. So if you stick to the end of the class, I'll actually cover this thing. Okay. So yeah, it should be dependent on n. So that is why big O of n would be a better notation to represent for this logic. That is why variable terming is more efficient, more classical, and expected by the interviewer also, or expected by you also to calculate. If you don't represent it like this, then you will face problem. Great. Okay. Now let us do something. So that we talked about notation, let us actually discuss the various sorts of notations. So in a problem, in a simple code forces problem, I'm not sure if you guys have opened up code forces, maybe gone through a problem, but I'm assuming just the best part for you guys. So you have looked at a simple problem. A simple problem is going to have obviously the question, whatever is required of you to do. And then of course it will have input, right? It is going to have some input. And of course it is going to have some constraint on that input. This is the word that we use, constraint on the input. Now what does this mean? Basically it means that, let's say the input is an array, for example, and that array has a total size of n. So the constraint on n means how much n can range from where to where. So it can be, the line would be written something like this, that 1 is less than equal to n is less than equal to 1000. So this is basically a constraint on n, which governs that n will be in this range only, that is 1 to 1000. Maybe you can have one more constraint and it will say that, okay, every number that is of the array ai will also have a range, that every number will be in the range from, let's say, 1 to 100. So this is a constraint that we put on the number also of each and every array. Okay, so this is what is classically given a problem. Now, why am I taking this is because now if I want to represent, like, if I want to represent the number of elementary operations in terms of n. So there are basically three types. Okay, there are three classical ways to actually do this part, and we'll discuss all. Having some test cases also means TC will be dependent on the number of test cases. Yes, it will. So that's actually the difference, which I think Aditya also rose, that sometimes it's like it is basically dependent on the number of test cases, because then you calculate the number of operations for every test case. But sometimes you don't bother about that and you only talk about every test. So actually show you a problem, and I think that will make much more sense when you actually cover a problem. Okay. Okay, so now there are basically three ways to do this. Let's take a quick example. So let's say the dependent factor is n, and n. So one way is called the at least way. What is the at least or least amount of number of elementary operations you would actually require? This is at least way. Then the other is at most. And then the final is average. So what is the at most number of operations you might require? What is the average number of operations you might require? So what we'll do is I'll do a small code over here. Let's say you have a for loop that runs in n order. Then inside that you have another for loop that runs from 1 to n. Okay. And then let's say this for loop closes, and then you have the final end over here. So now if let's say in this, like for all the people who might not be very aware with this for to for logic, I'll give you a very simple example. Let's say n was 5. So over here, what will happen is you can say that I would be running the outer for loop 5 times, and then the inner for loop also 5 times. So let's say the first outer for loop runs first time. In first time, it will run 5 times. Then it will run second time. It will run again 5 times. Outer for loop. Then outer for loop runs for the third time. Inner for loop again runs 5 times, and so on, so on, so on. Is this not going to happen? So a very simple thing can be written that it ran 5 plus 5 plus 5 plus 5 plus 5, that is basically 25, or 5 square, or n square number of operations. Yes? Does everyone agree? Yes? Correct. Now you have 25 elementary operations you ran, or basically n square number of operations that you ran. So you can understand that the time complexity for this is actually n square. So now if I ask you, what's the least number of operations you will do? What's the least number of operations you might perform for this? It's of course n square, right? If let's say I ask you, what's the at most number of operations you might do? Again, it's n square. Because you, girte padte bhi, whatever you are doing, you are still performing 25 operations. If let's say n was 5, or if whatever is n, you are still performing 25 operations. You are still performing n square operations. You're not going above that, but you're not even going below that. So at least is also n square, at most is also n square, and if n square is at most and at least both, then average also turns out to be simply n square. Does this make sense? Up till here? Now I'll actually change the parameter and it's going to make much more sense. Why did I take this at least, at most, and average thing? Okay. Now let's say right now I said that inside this inner for loop you were executing basically nothing. Let's say inside this you actually executed a very neat line of code. You, let's say, had a random function, and if you felt that that random function gave you a value of 2, you will basically come out of this whole for loop. So this random function is running in constant time complexity, just an assumption. And this basically random function gives you random numbers. And let's say that random number is 2. Then you basically come out of the whole for logic, everything, both for loops, you come out. Okay, so let's say this is the new updated code. Now things are going to be different. If I talk about at least, at most, and average, they're not going to look like n square anymore. Or not everything is going to be looking like n square. Why? Any guesses, guys? Any hints? What do you think is the least amount of operations you might do? N square will be at least. No, n square will not be at least. So at least, okay, so understand this. I'm not sure how do I spell this name. And Tekrish, so at least basically means कि कुछ भी हो जाए, whatever happens, इतना तो हो गई. Okay, whatever happens, itna to ho gayi. That means it's sort of the best case considerable. Yes, exactly. You are getting this logic. So I'll give you a very small hint. Let's say you enter the while loop, sorry, the for loop. Okay, fine, badhiya. Then you enter this again for loop. Okay, great. But as soon as you have entered this final if condition, in the first iteration only, the random function throws you a 2. What happens then? You basically come out of this whole for loop. What is the amount of operation you performed? Can you say I only performed one iteration, right? I took only one iteration and my logic ended. So can I say that my at least or the best case operations that I took were only one? Make sense, guys? Thank you, Aritra. Does this make sense, guys? So we can say that the at least amount of operations we have performed is one. Now, talk about at most. What is the worst case? What is the highest operations I could have performed? Of course, let's say you ran this for logic, you went inside, then inside again, and so, and never this random function gave you 2. ऐसे भी तो हो सकता है ना? This is a random function, so it doesn't give you 2. It doesn't give you 2 any time. So that means you will have to perform all n square operations, and only then you will come out of the for loop. So can I say that the at most turns out to be n square? Make sense? And then of course, if I have average, if I want to average this, basically n square plus 1 by 2. So roughly this is average. Is this clear, guys? At least, at most, and average. Very, very important. Okay, cool. Okay, let's move on. So now that we have understood at least, average, and all, we want to classify them. This was all that was to understand logically. How do we classify this theory, and what do you remember? What do you take away from this class? So takeaway from this class is actually to first and understand that these three sorts of ways of time complexity are actually called something. One is called big O, which is the most classical one. Other is called theta, and then this is called omega. What is big O? Big O is actually the representation with O of, let's say, I'll just take a random variable, let's say n. So big O of n is actually represent, like big O of n notation represents O with an n. When you talk about theta, it is represented by the theta variable and then n. And when you talk about omega, it is this omega symbol with n. So this is the representation. And what is actually big O? Big O is actually that at max, or you can say worst, or you can say upper bound. Okay, upper bound, or you can say highest number of operations you might perform. This is called big O. Slide is not visible. Oh, okay. I'm so sorry. So sorry. I think my present failed. Thank you for letting me know. Visible now, guys? Cool. So I'll put a small. So despite two of outer and inner loops, we will consider this as, we'll consider it only as one operation if you actually have this rand function going on. Okay. If this rand function gives you two, it's fine. Okay. So as I was repeating, the three types are actually called big O, theta, and omega. To represent them, we use big O as O of n. Theta is known as theta of n. This is the symbol theta. And omega is this symbol and n. So again, I'm taking n as a general factor. Maybe it can be n square something. Uske andar kya hai, it doesn't matter. I'm just representing ki what will be you putting outside. If it's O, then it's big O. If it's theta, omega is omega symbol. Okay. Now, what is actually big O? Like when I say what is the big O time complexity, is basically this at max or worst or upper bound or highest time complexity that we talk about. What is actually theta? Theta is actually the average time complexity that we talk about, average or middle time complexity that we can say. And what is omega? Omega is actually the best or the at least time complexity that we talk about. Okay, is this clear, guys? So when I say that, now important question of course would be that, okay sir, I'm sitting in an interview and that interviewer is going to ask me that tell me the time complexity. Then should I ask that person, do I want to report the time complexity in big O, theta, or omega? Should I do this in the question, in the interview, or should I do this while I actually solve the problem? No, that is actually the catch over here. I'll give you a small story. Okay, tell me if you can follow this. Let's say that there is a guy. I'll draw a small stick figure, and this guy has a small gun. Okay, this guy wants to shoot you. Let's say there are 10 boxes. Okay, let's say there are one box, one box, one box, so on, so on, so on. Let's say there are 10 boxes. Let's say हर एक box में there are some number of toffees. The lowest amount of toffees in the box is 1, and the highest amount of toffees in the box is 10. Clear? Is this story clear? There is a guy. He has a gun. He wants to kill you. In front of you, you have 10 boxes filled with toffees, and you can have minimum 1 toffee or maximum 10 toffee in every box. Now, let's say this guy says that I want to kill you. Tell me an x value. Tell me an x value. This x value is going to be the amount of toffees I will find less than equal to in every box. If you say that this x value is some x, like if you quote this x value, and in any box, I find the amount of toffees less than this x, then I will kill you. Then I will shoot you. You're dead to me. Now, you of course want to save yourself. Yes, you of course want to save yourself. So what x should you tell? Like you can have toffees ranging from 1 to 10. Will you say 5 toffees? Will you say 6 toffees? Will you say 1 toffee? Will you say 10 toffee? What do you think is the best thing? What will save you? Will you not think this to yourself that, okay, in the worst case scenario, every box can have 10 toffees. So if I quote x to be 10, then I will be safe because 10 se bada to kuch hai hi nahi. There is no bigger than 10 in the box in number of toffees. Every box has maximum 10 toffees. So he will always find at least 10 toffees in the boxes. He will never kill me. So what did I do? I took the worst case possibility to save myself. Yes, did I not do this? And I'm safe. This guy doesn't kill me. So we apply the same logic actually when we code, when you talk about online judges. When somebody asks you the time complexity of the question or the solution that you create, you never try to tell, okay, the average time complexity of the solution will be this, or the best time complexity of the solution will be this. No, you always say the worst time complexity of the solution will be this. And that is why, since worst case time complexity is known as big O time complexity, we always prefer to report our logic in big O notation. Now, is this clear? Yes? Wow moment. Fun, guys? I'm assuming the box contains 0 means worst to best. No, no, like I just tried to pitch up a story. It's basically like the idea is that because you are performing some operations and you are getting some input from the test case, you will not want to take the average or the best case. Rather, you will want to think of the worst case that could have happened in terms of your input. Because ho sakta hai that it can happen that the platform gives you very big inputs. Okay, that's the worst thing. It gives you very, very big inputs. But you have created a solution for which the average time complexity is less. So you will say, oh, this should work. This should not get me a TLE, but it will actually give you a TLE because you did not consider the big O notation. You only consider the theta notation. Okay. So this is it's basically called preparing for the worst. If you prepare for the worst with terms of your code, you will be good to go. You will not get a TLE. Okay. Now, I'll put a small comment on how is this represented fact done on a graph of time complexity. So everyone understands like a general 2D geometry, right? If let's say this is the input, and let's say this is the time. So what can happen is I can draw an input line. Let's say this is the input. And let's say the solution is running in n square time complexity. Then if I'm drawing after 0, that is origin, then the time can be like this. Yes, you understand a parabolic curve. It's sort of like this. So I've just drawn something that's after positive x-axis. So this is the graphical representation of what do you mean when we say function, like when we say time complexity is a function, this is the meaning of that. When we say time complexity, or time is basically a function of input. Assuming you had an n square time complexity, if you have this much amount of n, then you will have this much amount of time complexity. Sorry, not time complexity, time. So it's like a general representation of what we do in time complexity. Okay, I hope this is clear. Any doubts, guys, till now? I hope everything is going fine. Okay, I think I should move on. So again, we covered everything in this part. Big O notation. Big O notation of an algorithm is a function to calculate the worst case time complexity of an algorithm. It is written as big O of whatever is the worst case time complexity. Now it is used to calculate the approximate upper bound. That is what we commented over here also. So upper bound is again an English term. Upper bound means sabse zyada kya. What is the most boundary of upper format? It's basically upper bound. And it's used to calculate the approximate upper bound of the algorithm. It expresses how the runtime grows relative to the input. So this grows relative to the input is something I've shown you with the graph. If you have this much input growing, then this is the relative growth. More convenient and useful than other notations, of course, because as we discussed, big O notation is actually what governs the whole idea. Omega and average, like omega and theta notations don't govern the idea. If you know that, it's fine. It's extra knowledge. Maybe the interviewer asks you, you are going to get, of course, brownie points. But then when you actually want to report the time complexity, don't report it in omega or theta time complexity. Always talk about the big O notations. Okay, cool. Now, we have very, very acute rules that we actually follow for big O notations. Let's actually discuss them. So, rules for big O notations, we have 4 rules. Should not have constants. What does this mean? So I'll give you a very, very simple logic. Let's say you have a for loop and it runs in n order. Then you have another for loop and this runs in, let's say, only 4 times. So you have one for loop, outer for, this is again not inner or outer. This is 2 separate for loops. Okay, one for loop, then another for loop. Uske just niche, when it ends, another for loop. One is running in n order. That means it's dependent on the n variable. You are running from, let's say, I1 to n. So n is something you input. But the other for loop is only running 4 times. It's constant. So now if you actually report a time complexity, or sorry, if I ask you, computer, how much will you be running the elementary operations? The computer will say, okay, I am running n operations. Then added to that, I'm running 4 more operations. Yes, so this is n, this is 4. So technically, if this is true, then should I not report my time complexity as O of n plus 4? I should. But conventionally, again, remember, I'm talking about convention. This is not, I'm not saying that if I don't have a constant in my time complexity, that means the computer is omitting it. Computer is, of course, going to process this for loop also. But when we talk about conventional term of telling the big O notation, you don't involve constants. So this n plus 4, this plus 4 variable is going to get dropped, and this should be written as only O of n. Okay, like I'll remove this. N plus 4 should be converted to O of n. Any problem, guys? So we should not have constants. Again, this is convention. This is no if and but in this. Okay, now should not have constant factors. Now this is a very important thing. Like it, first of all, this might be a confusing point that first we discussed constants, then we are saying constant factors. What's the difference? Can anybody tell me what's the difference? What is the difference between constants and constant factors? I mean, of course, the word over here is factors, right? Okay. So I think anybody can guess this part rightly. That okay, so no idea, Ravikant. Okay, so Ravikant, I'll tell you. Constants basically means the things you actually plus or subtract. And factors actually mean the things you multiply or divide. Because it is factors. Okay. Meaning, let's say, Ravikant, let's say that your time complexity was O of n by 2. Let's say you calculate time complexity to be n by 2. But conventionally, you will not report it to be n by 2 because this by 2 is a constant factor. So you will say your time complexity should be written as O of n. This by 2 will be removed. Do you understand this, Ravikant? That is the difference. So over here, like the above thing we saw was n plus 4, that is the constants. And this by 2 or could have been into 2, into 3, into 10, whatever, that was the constant factor. So we remove both of them and none is reported when we conventionally report the time complexity. Okay, great. I hope this is clear. Third rule. So I think we have covered 2 rules. Third rule. Only include the fastest growing function for each variable. Now, let's say your time complexity is given as n cube plus n by 2 plus n square. The convention will say, don't report your time complexity as n cube plus n by 2 plus n square. Why? What it will say is that in these 3 different functions, n square, n cube, n by 2, what is that function which is growing the fastest with terms of or with relative growth as n? If n is, let's say, 10, then will n square be a larger value, n cube be a larger value, or n by 2 will be a larger value? Which is going to grow faster? Obviously n cube, because it's the larger function. Yes. So what will conventionally big O notation say? That for a single variable, in terms, right now we are comparing only n's, only report a time complexity in terms of the largest factor. So this will actually convert to O of only n cube. We will not bother about n by 2 and n square. Now, I'm again, remember, that's what I'm trying to focus all the time. This is convention. This is not that computer is ignoring n square and n by 2 operations also. This is convention. How do you report it? It's given at n square. Sorry, n cube. So this is the third rule. And of course, a fourth rule is like basic common sense. This is something I could have not discussed. Can never be 0. Of course, you cannot run a logic and you can be like, oh, this ran in 0 time complexity. That doesn't make sense. There has to be at least O of 1 time that runs, or constant time is the least amount of time any algorithm has to run in. So it has to be at least O of 1. Okay. Now, guys, a fun quiz. This is our example function. We want to reduce this down. So in this, you have basically two variables now. You have one variable that was n, another variable was m. Now, quickly tell me, guys, in the chat, what do you think is the final big O notation of this function if I want to represent this? So understand this, that we have 2 into n square. All right. So of course, when I write 2 into n square, we will want to remove this 2 because this 2 is a constant factor. Similarly, we have 4 into n. So we'll want to remove this 4 because this is a constant factor. Then we have 4 into m cube. So we want to remove this 4. And then we also want to remove this plus 5. And then we also want to remove this plus 10 because this is all constant factor and constants. So overall, I'm remaining with n square plus n plus m cube. But even in this, if I compare n square and n, I will prefer to take n because n square is the larger growing term as compared to n. So my time complexity turns out to be O of n square plus m cube. Srinilia, yeah, you're correct. So Ravikant, we don't write n cube. Why? Because Ravikant, understand this, that you have two different variables in the time complexity. What can happen is, let's say n was given 100 and m was given only 10. If n is given 100 and m is given 10 in your test case, then what do you think is larger, n square or m cube? M cube will be 1000 and n square will be 10 power 4. So 10 power 4 is larger. Yes. That is why in this case, n square is being the larger term. But maybe I create a case where n is 100 and then let's say n is 10. Now m cube is larger. So that is why I cannot beforehand deduce which is going to be the larger term because both are different variables, right? When I had n square and n, I removed n because I knew both were same variables. Remember, include for each variable. Same variable पे मैंने fastest growing term लगा लिया. But when I'm talking about n and m, they are different. So I have to consider both of them in my time complexity. Okay, clear, guys? This should not be a doubt. Should we move on? So quiz number 2 for you. Now k is a constant. Tell me, what do you think is the final big O notation that we should do? One, n plus m by k. So k is a constant. Correct. This should be O of n plus m. Very simple. What about this? N into n plus 1 by 2. So basically this means you have n square by 2 plus n by 2. इसमें से we can of course remove first of all by 2 things. So this is n square plus n. And then we can take the bigger term. So this is O of n square. Correct. Okay. What about the third example? Now I think this is a typo over here. I'll just quickly correct this. This is m, sorry, this is m square n and this is m n square. So n and then this is I think m. N plus mn square plus m square n plus m. Does this make sense? Hi Akshat, hello. I hope you're doing great. M square n square. No, not m square n square. So you have a term that grows in mn square. So you have a degree of 3 order, right, Shonbit? And you also have a degree of 3 order with m square n. As compared to n and m separately, this is a larger degree. So I can take both those degrees and this is the final answer. Okay? And what about the fourth example? O of n cube by 64? No, not by 64. Plus 20n is basically n. I can remove that n because in front of n cube, n is nothing. And then you have 32 square, which you can remove, it's a constant. You can have n cube n square m square. Now, preferably, we would tend more towards this side, but then it's fine to write n cube over here. Okay? Great. Let us move on. So now that we have understood our, like we have done a quiz also, we have understood the rules of big O notation, how do we reduce, how do we calculate the time complexity of an algorithm? So normally like up to your level and whatever starts with beginner level, even up till level 2, and again, this doesn't govern till level 2 also, this goes even further. It just deepens the knowledge. Normally time complexity comes from loops and recursions. Like 90% of the logics we create, they have time complexity that is governed by loops or recursions. So if you understand loops and recursions, you will obviously understand the time complexity quickly. Now, recursive algorithms is something we don't cover in level 1, but of course, you can definitely check that out for level 2. Anybody who prefers to understand recursion and other topics like bit manipulation, prefix sums and all, you can go for level 2 in this case. And loops is something we do in level 1. That's the most basic rudimentary thing. So time complexity, how do we get that from loops is something we'll look now. Okay. So again, more quizzes. Calculate the time complexity of an algorithm, and there is a nested loop. So when there are multiple nested loops, we multiply the expected number of iterations of the loops. We actually saw this in the example also when we calculated n square, right? So I think this should be very, very clear. Can you guys quickly tell me what do you think is the time complexity here for this example? N square, correct. Great. So this runs in n order. This runs in n order. And this basically runs only 4 times because this is a constant, 0 to 4. So you have something that looks like n into 4. You can drop the 4, this becomes n into n, which is simply as O of n square. Yes, good to go. This is the first example. Let's move on. Second example. What do you think is the time complexity, guys? So this runs in n order. This runs in n by 2 order. So you can multiply both. N into n by 2, which is O of n square. Because we can remove this by 2 factor, and I know this is n square. Yes, I hope this is clear. Very, very simple. All right. Again, pause me, guys. Ask me any doubt you have in the chat. I'm looking continuously at the chat for your answers. Okay. Okay. Example 3. Now this is actually very fun. You have a loop that runs from 1 to n, and I is multiplied by 2 every time. So let's say I is initially 1, then it's 2, then it's 4, then it's 8, then it's 16, then it's 32, and so on, so on, so on. What do you think is the time complexity for this? Very, very unique thing. I hope you learn something from this. N, no. Log n, great. So specifically zero gravity, do you think it's log n or this is log base 2 of n? That's a very, very important thing. Log n is like basically typically it's like log e or log 10. Base is also very important. This is technically log base 2 of n. Okay. Why? I'll give you a quick proof. So let's say that your I was 1, then it became 2, 4, 8, 16, so on 32. Till when did this happen? ये कब तक हुआ? What is the stopping point? Of course, you stopped at a location till which you were less than n, because after this you went above n. So you stopped at a location which was less than n. Now, if I am able to count this much length of segment, will that not mean this is the length or this is the number of times this for loop runs? Of course, because it became 1, then 2, then 4, then 8, then 16, then 32. Where did it stop is the number of times I'm counting. 1, 2, 4, 8, 16, 32. Okay, stopped. Okay, 5 iterations. Great. So this is something I want to count. So I'll generalize this. Let's say that this is 2 power x term. Now you can understand that all of these are 2 powers. So let's say this is this 2 power x term for which you were less than n, and just above this, if you go in the next iteration, you actually become greater than n. So 2 power x is the last value for which you are less than n. So I can write this like this. 2 power x is less than n. Now by log properties, I can take log base 2 on both sides. That is 2 power x is less than log base 2 of n. And now by log properties, this x expression can come out and log base 2 of 2 will actually become 1, which means you will get indirectly something that looks like x less than log base 2n, which means that x is this final typical value of log base 2n, after which you will stop, which means this for loop is going to run maximum log base 2n number of times. Clear, guys? Is this proof clear? Okay. Example number 4. So this is running from 12 to n minus 123. Very, very like typical values. Then inside it's running from 6 to n into 2. And then this is running in 4023 to 23. So this also runs in n order. This runs in m order. And this sort of runs in k order, but then k order is constant. So can I write this as O of n into m? Yes. Cool. Okay, I hope this is clear. Now, the main thing that we were waiting for, I think we have covered almost 3 of our goals. Our final goal, what is the cheat sheet? So here we go. You guys can take a screenshot for this. Okay, I mean, this is nothing unique, nothing I've created on my own. This is something we typically have in good competitive programming books and everywhere. So this is a small cheat sheet. Now, this is actually the main thing people imprint in their minds, good competitive programmers imprint in their minds, so that when they solve a problem, it helps them understand algorithms. Now, at your level, I understand that you might not be aware of all the algorithms. Like you might not be aware of, let's say, for example, let's say you're not aware of insertion sort, or you're not aware of binary search, or maybe you're not aware of permutations of a list calculation, something like that. It's fine. The point is, as you grow in this journey, you will of course come across a lot of algorithms, and how do they solve problems. Now what will happen is, when tomorrow you solve a problem and you know in the back of your mind that okay, if there was an x logic and that x logic required y amount of general operations to run, if this is something you remember, and then you have also in your mind this table, roughly estimation of this table, then what will happen is you will be able to guess quickly that in this problem, can I apply this logic or not? For example, let's say you are solving a problem and n turns out to be 10. So I know that of course you can apply a logic that is an O of n solution, because O of n will work. You like maximum is 10 per 8. So O of 10 will work, of course. But you could have also, if required in the problem, explode a possibility. AI was suggesting Hungarian algo. Oh, okay. So yeah, you could have also explored a possibility that all the permutations of a list, this sort of a calculation algorithm requires n factorial. This algorithm requires n factorial calculation. Now, because n is given 10, maybe I can run a solution that runs in even 10 factorial order. 10 factorial is roughly some value which is less than 10 power 8, by the way. I'm not sure of the value. You can Google that out, but it's less than 10 power 8. So now what will happen is when I'm looking at the problem and I'll be like, oh, n is that small. Maybe I can run this sort of a logic also. It will work. And this is going to help me create more ideas. This is going to expand my horizon. Okay. Now, it will help you in the other vice versa case also. Let's say n was not 10. Let's say n was 100. Now, in 100 order, you of course cannot run n factorial, right? Because 100 factorial is a very big number. It's actually much, it's like 10 power 10, 100 order. So it's not in 10 power 8 order. So if n is 100, then even like, let's say you were sitting and you did not know the time complexity of this, or you did not know how do you calculate expected time complexity, maybe you could have written a code of permutations of a list and then later realized, oh, this is not working. This is going to give me a TLE. But somebody who knows this sheet, somebody who understands time complexity, even before starting the logic, will imagine in his head that if I write this code, it is going to run in 100 factorial order, which is not going to work. Don't care about this logic anymore. I'm not going to talk about this. So this helps save time, and this helps create more and more ideas and removes redundant ideas from my head. So it basically guides me in the right direction. This is actually the cheat sheet. How many of you like this? Guys, tell me in the chat. Fun thing? Okay. So like this is a rough approximated order. Like let's say you have something like a 400 order, or like basically like a 10 power 2 order. You can run solutions that are in n cube. So n cube order are solutions that, like, one of the very famous solutions that runs in n cube is multiplication of matrices. So if let's say you have a matrix question and you're under like matrices question and you're trying to guess that can you run an n cube solution or not, you will if you think that the order of n is 10 power 2. Okay, let's say you are in 10 power 3 order, something like 5000 order. Then bubble sort, insertion sort, all this will start to work. If you are in 10 power 5 order, n root n will start to work. In 10 power 6 order, n log n will start to work. All right. If you are in 10 power 7 order, O of n will work. 10 power 12 order, root of n will be preferred. And if you are in 10 power 18 order, that's the very high order, now you will be preferred either you create a log base 2 solution or you create a constant solution. And this is very, very important. Specifically, like I have myself experienced this part and this part to be very true. What happens is if I look at a problem and it's in 10 power 6 order, sometimes I try to think, why can I create a solution that runs in n log n? And then I start thinking binary search and it works. Similarly, if I have a very large n that is in 10 power 18 order, that means it is required for me to create some sort of a constant time formula, which means some mathematics. Some mathematics is required in this problem so that I'm able to arithmetically calculate the answer quickly. So it gives me hints. Okay, 10 power 18 is such a high order. Think mathematics. Don't think binary search. Don't think a brute solution. Don't think a for loop. Think mathematics. This tells me, this gives me the hint. And because I know this, मेरा सारा time उधर जाता है. I invest my time rightly in the right direction and I get the problem much more easier, much more quicker. Okay? Clear, guys? So this is a cheat sheet. You can take a screenshot. I hope everyone has done it. Final points to know. This is when we can end. So identify the variables that contribute the time complexity. Of course, this is something you have to do. If you're not able to identify n and m, then what is the problem? You are left with nothing. Okay, so if I take subscriptions in level 1, on level 2, it is going to help me clear DSA rounds. Okay, so I'll come to this question. Let me just complete this and we'll take like last 10, 15, 20 minutes for all the doubts. Okay. So identify the variables. Of course, this is very important. If you're not able to identify variables, then it's no big deal. Okay, you need to identify n and m and what's actually the variables that are coming in the logic. Then, of course, this is a very important point. Just because constraints allow you slower solutions doesn't mean we cannot optimize this. This is actually very important for interviews. Like what will happen in an interview is the interviewer is going to say, okay, n is 1000. So you will say, okay, maybe I'll run an n square solution because n square means it's in 10 power 3 power 2, that's 10 power 6. It's less than 10 power 8 order. Great, good to go. I'll make it. But what if this solution could have been optimized to O of n? O of n will also work because O of n, of course, is faster than O of n square. So the interviewer might not give you a hint directly, but since you are creating an n square solution, it doesn't mean if n square is working, O of n solution was not a possibility. So don't make this a point to yourself that if I want to, like, only should I solve the question is my target, you should also try to understand that what's the best optimum solution to this question. Maybe for this current n in the problem, n square was fine. But if I knew, or it could have expanded my knowledge for an O of n solution, why not also learn it? It's going to help me. And this is the main idea. If constraints allow slower solutions, fine, create it for the contest sake. But after you upsolve or after you look at the problem, do make sure that you also understand the optimized way of actually solving that problem. Okay. Now, this is actually the final line. Test cases matter unless there is a limit explicitly imposed in the constraints. So this is a very, very important topic. I think I told somebody I'm going to clear this part. I'm not sure if that person is still in my chats. Okay, so Aditya asked this. Aditya, are you still in my chat? So Songwith, yeah, great. So I'll just tell this anyways. So what happens is, this thing is, like, I'll give you a very small simple thing. Problem में क्या लिखा होगा? What will be written at the top? It will be written that, okay, let's say there is, like, for time limit per test is, let's say, 1 second. So you will say, and now inside this it will be written that every test has, let's say, 10 power 3 test cases. So now test cases will matter. Why? Because for every one, like for every test file, or basically one test, you could have done 10 power 8 elementary operations because it was allowed 1 second. But inside every test, there are some test cases. So if I ask you what's the number of operations you actually perform for every test case, that would be 10 power 8 upon 10 power 3, which is 10 power 5. Which means if I now talk about the number of operations allowed for every test case, this changes. This becomes 10 power 5 order. So that is why test cases matter unless there is a limit explicitly. So what's the limit? What can happen is, like, this is a very general problem. This is the general way of how they give a problem. But if they want to make sure that you don't calculate the number of operations for every test case, rather you talk about only the test, they will give you something like this. That is, sum of all n over test cases is not above, let's say, for example, 10 power 5 order. This is the line that they're going to give in the constraints. And this is the limit. What will this mean is, let's say you had 10 power 3 cases. So let's say this was the test case 1, test case 2, test case 3, test case 4, so on, so on, so on. Every test case has some n1, n2, n3, n4. If you add everything up, this is not exceeding 10 power 5 order. So now if you want to create a solution, don't create a solution that is boundary, like on the boundary of every test case. Rather compare this with the test that is 10 power 8. So now your variable to compare would be this. If the limit was defined, then it was, like, if it was not defined, it was this. Sorry, it was this, that is 10 power 5. But because over here the limit is actually defined, then you will compare with 10 power 8. This is the meaning. So this is the differences which comes in terms of time complexity. Okay. So of course you can, like, when you come across a lot of problems, you will see this happening and you will understand over there. And the final point, constants and constant factor removed when calculating big O still matter. So this is very important. Okay. Right now, when we were talking about the convention, like, this is the same thing I actually repeated. It's something, and this is not new. I said this again and again, that what will happen is, when you report the time complexity in conventional format, you want to remove the constant factors and everything. But in a computer, the computer is not removing them, right? If you write this +4 or by 2, computer is of course going to perform that many number of operations more or less, or whatever happens according to the factors. It's just that you are representing them conventionally. That's why you might think they don't matter, but they actually do. So always think this in your head, that although you're reporting them, always make sure in perspective of computer, the computer will actually execute them. So they removed in conventional sense, but still matter with POV of a computer. Okay, so this is the final point. Now, like, I have attached, I think at the very end I attached some important links and some problems also. We'll see if we can hand you over this PDF at in the description of the whole live. All right. So I think this is everything that we have covered. Uh, so yeah, great. I think we have covered everything. Now I think the floor is open for doubts. So if you guys have any doubts to me to ask, we can take them quickly, and then we'll be ending the live. I hope this was a fun demo class for you guys, and this pushes your interest in CP overall. Okay, so I saw a problem there was 10 per 9 plus 7. Now it's clear. Okay, great, Songwit. So I think that's clear. Thanks. Thank you for joining. So any doubts, guys? If you have, please let me know right now, or you can ping this in the comments later on of the section, and I'll of course be replying to everything. Okay, so definitely check out the courses. Check out. So I'll be part of level 1. Level 2 is going to be taught by another a very good educator of ours. Level 3, level 4 again, same thing. So see what level you are currently in, what topics are something you want to explore in a level, something that you haven't explored as of now. And I think that is going to be a very good deal. So if you have an interest in CP and everything, do check this out. Okay, so I think we have no doubts. Thank you for joining this stream with me, and looking forward to meet you guys in TLE level 1. Okay, yeah. Sorry, I think I had to take this out. Yeah. So it's gonna help me clear in DC rounds interview, but as we know, CP journey is different, and I'm new to it. So again, Shri Nilaya. Okay. What happens is you have a lot of topics that we cover in level 1 and level 2, and they're kind of part of DSA only. So when we talk about DSA rounds, that is this online assessments that happen. I can guarantee you, like, this is not at all a question also that they are not going to help you. They are of course going to help you, because what we teach and what we like give out in the DPPs and in the doubt supports and everything, they actually help you grow. They help you grow and look into problems in a brighter format, in a broader format. So it's very obvious that when you come across competitive programming problems in the online assessments, you will have much more hands-on experience, because you will have you will have more speed to solve because you have practiced. You will have you can read questions, bigger questions fast, because normally CP questions are a bit larger in length. So wo sari practice, all that stuff is going to help you actually in the DSA rounds, of course, right? And when we talk about being newbie, then that comes, of course, this is very dependent on what level right now you are in. So as I mentioned, you can explore the course. If you feel that level 2 resonates more with you as to your current level, your current knowledge, you can of course take up level 2, or you can take up level 1. But I can guarantee both levels are indirectly going to help you, whichever level you take, because you will of course have a lot of stuff to explore in that. Okay, great. So thank you everyone. Thank you for joining. I hope I was able to provide some value to your time. All right. Bye bye. I'll stop this stream now. Thank you.